All right, that's great. Thank you for the really wonderful introduction, Justin. It's great to be here, and thank you also to Laura. So this is my third trip to Blacksburg. Serkan and I were reminiscing that my first, I think, was in 2004, 2005, when Serkan and I had first met, and we spent most of the time in a room with a blackboard in the old math building, and actually got a paper done in that week. The second trip, I was here to give a talk in the CMDA Distinguished Lecture Series. And then on this third trip, it's really been wonderful to see the old friends that I already knew in math and aerospace engineering, but also to learn about the National Security Institute and meet a whole lot of new people. So really wonderful to see how strong the community is across Virginia Tech. And as Laura mentioned, just being out there in the hallway and seeing mathematicians and aerospace engineers and people working in national security kind of colliding. These are the things that are very near and dear to my heart as somebody who is very committed to interdisciplinary research and education. So thank you for having me here. Today I am going to talk about the topic of digital twins, something on many people's minds. And I have to warn, I've already warned a number of the math faculty. There's not a whole lot of math in this talk, because I knew it would be a very diverse audience, so it's really at a little bit higher level. But if you're interested in the nitty-gritty details of the math and the computational science that sits underneath some of what we're doing, definitely would be very, very happy to talk with you about that afterwards. All right, so here's the plan for today. Just start a little bit actually with just even the question of what is a digital twin, or maybe some of you would ask it as what is not a digital twin. Talk about some of the foundational research challenges. And in the first two parts of the talk, I will draw a lot on the work that came out of the National Academy study that Justin mentioned. Then I'll dive into a little bit of the work that goes on in my group, and in particular, how we are using graphical formulations as a way to think formally about digital twins, and how the graph models really provide both a mathematical and computational foundation for building digital twins. And then I'll give just a couple examples. I picked, Zoom wants to update. No. The University of Texas Information Security Office was following me everywhere. Let's try and snooze it if I can find my mouse. Hang on, I got to find it. We got 4 minutes and 47 seconds. And a countdown. Oh, here we go. There's my mouse. Snooze. All right. It's good. Drew, we've got a lot of work going on in my group. I should say that most of my own expertise is in aerospace systems, and a lot of the work we've done in digital twins is for unmanned aerial vehicles, which is really more in my comfort zone. But I picked a couple topics outside of my comfort zone where we're collaborating with other domain experts, really just to try to highlight, I think, what some of these foundational challenges are and how they cross-cut fields. And I really hope, especially for the students in the audience, that you'll leave the talk with some ideas about questions. What are some of the important questions that need to be tackled by the research community in partnership with domain experts? And second, what are some of the solutions? What are some of the technologies that are actually out there, maybe residing in engineering and math journal papers that actually could come to bear on challenging problems? All right, so let's start with the question of what is a digital twin? How could we define it? And for those of you who don't know much about National Academy studies, these studies are very big and formal efforts where a big part of the study is information gathering. So this information gathering in this particular study went on for almost a year, where the committee hosts information gathering sessions where experts are brought in. We hosted, in this case, 3 different workshops covering engineering, biomedical applications, and climate and atmospheric sciences. So there's a lot of work and a lot of community input. And right off the bat, we were sort of faced with the question of how do you define a digital twin? And throughout that year, I heard many different definitions of digital twins, including completely conflicting definitions. Now, of course, there's not going to be one definition that everybody is going to buy into, but we nonetheless thought that it was really important to try to have a definition that would cut across and apply across many different domains. And so this is the one we came up with. And this definition actually very heavily builds on a definition that was published in the aerospace engineering community, where a lot of the initial work in digital twins has been done. And that definition in itself was the result of a lot of community effort. So here it is. A digital twin is a set of virtual information constructs that mimics the structure, context, and behavior of a natural engineered or social system or system of systems. I cannot tell you how many hours we spent debating natural engineered or social system. It turns out the term physical system is a no-go for some communities, which really surprised me, because as an engineer, I would talk about things being physical systems all the time. The virtual information construct is dynamically updated with data from the physical twin, has a predictive capability, and informs decisions that realize value. The bidirectional interaction between the virtual and the physical is central to the digital twin. So we really tried there to capture the essence of what is a digital twin and how is it different from the modeling and simulation that many different communities have been doing for many decades. And so this kind of leads into this, this graphic, which is in the study report. And one of the key findings, which is we did hear from many corners, oh, digital twin is nothing but a fancy new name for simulation and modeling. What we really concluded is, yes, a digital twin builds on modeling and simulation, but it's more than that. And as we start to parse all the different elements of that definition, and we look at it here graphically, okay, here on the right is the virtual representation. So this is the modeling and simulation. This virtual representation might be physics-based models. It might be machine learning-based models, statistical models, empirical models. Likely it's going to be some combination of all of those things. Over here, we have the physical counterpart, and we could be thinking about an engineering asset, an aircraft, a spacecraft, a building. We could be thinking about something in the biological world, maybe a patient or a human. We could be thinking about something in the natural world, a farm, a forest, a coastal region, an ice sheet, maybe even planet Earth. And what you'll recall from that definition is we really drew out this bidirectional interaction between the physical and the virtual. So this is where the digital twin really goes beyond just being a virtual representation. So from physical to virtual, this is where we are collecting data. We're making observations of the physical world from sensors, from remote sensing, maybe human observations, and feeding those in to update the virtual representation so that the virtual representation is, first of all, representing the particular physical counterpart, the personalized model, but also so that the virtual representation is really dynamically evolving as the physical world is changing. So mathematically, this is an inverse problem, or the process of data assimilation. And then the flow from virtual to physical, where we're now taking this virtual representation and using it to drive decision-making, meaning solving some kind of control problem, or maybe making a decision about how to guide future data collection, so an optimal experimental design problem. So, but driving changes in the physical world. And then you sort of have this idea that it's this back and forth. We're continually making observations from the physical world, updating, using that to drive decisions, which cause additional changes in the physical world, and this bidirectional interaction continues. What you notice in the middle is something that I think is often not highlighted, which is while there are many applications of digital twins that may lead to fully autonomous or automatic decision-making, there are maybe many more applications of digital twins that will have a human in the loop. And so the question of human-digital twin interaction and human-in-the-loop decision-making is absolutely essential as we think about what is a digital twin and what are some of the challenges. And then lastly, if we look at the arrows going around the outside of this diagram, we have the challenges and the opportunities of verification, validation, uncertainty quantification, security, and ethics that are all challenges that really encapsulate everything that goes on in the digital twin. And now all of these topics, right, verification, validation, uncertainty quantification, VBUQ, this has been a long focus of the community for modeling, for virtual representations. But as I'll get into in a second, as we start to think about the digital twin as being more than just this part of the picture, but really the whole thing, the questions of VVUQ become more complex because there are more pieces that we have to consider. So it's kind of exciting to think about this, to think about how digital twins can really combine models, data, and decisions in new ways to really drive better decision-making across systems. One of the other things that we talked about a lot is how one thinks about a digital twin and what the role, particularly complementary roles of models and data are in a digital twin, and also what role there is for AI and machine learning. And so in talking to many people and you sort of ask them what sits at the core of a digital twin, often the answer that you will get would be data, right? I think this is true, and this is true in some of the best examples that we have of digital twins. For example, the digital twins that are guiding predictive maintenance for aircraft engines today, really in operation. There are tons and tons of data generated in those applications, and the data really are the core of the digital twin. And as we take the data, we think about wrapping that data with some kind of numerical model, maybe a machine learning model, maybe some kind of statistical model, putting analytics around that, and then using that to drive decision making. So that's certainly one view of a digital twin that fits well for many applications. But there are many applications where you don't have reams and reams of data that truly cover the space that you need to drive decisions, especially when your decisions are based on predictions for conditions that your system has never been in, predictions about the future. And so in those settings, we really have to think about the mathematical model that will be at the core of a digital twin. And Mark and I were talking about this at breakfast. Somehow a lack of appreciation of the importance of dynamical systems that give us laws that describe how complex physical phenomena evolve in space and time. So the mathematical model could come in many forms, but certainly in many applications in engineering, I think in the sciences, that mathematical model may be a set of a dynamical system, a set of differential equations, wrapped again with a numerical model, which could be a more classical discretization of governing equations, but also could be something employing machine learning. Then the data come in now through the lens of this mathematical model, so solving an inverse problem where you're not trying to just characterize based on the data alone, but rather recognizing that the data are informing this mathematical model that you've put at the core, and then using that to drive decision making. So it's not that one is better or worse than the other. These are just different ways to think about a digital twin. And I think it's very, very important if you're embarking on digital twins in a particular context to really think about what you have. Are you in a realm where you have a good, solid mathematical model where conservation, mass, momentum, and energy are essential to making predictions? Or are you in a realm where you have a ton of data and you really don't have a good model, maybe a biological system, to be very intentional about the architecture of the digital twin? So let me transition a little bit into talking about some of the research challenges. And again, when you see the slides in this format with the Academy's logo down here, these are things that came directly out of the report. One of the key findings in the report was that the publicity around digital twins currently outweighs the evidence base of success. So this is a very diplomatic way to say that there's a whole lot of hype out there. I do feel like the hype has settled down. The report was issued just over a year ago, and maybe I've become immune to it, but I feel like the hype has settled down just a little. We talk in the report about the importance of distinguishing between the aspirational and the actual. We can all imagine a digital twin of something that would be just life-changing. We can all imagine the day when one day we will have digital twins of ourselves, and our digital twins will guide decisions we make every day, like what we eat, whether we exercise. And it's aspirational and exciting to think about that future. But we also have to be realistic and say that we are very, very far from having that today. We just cannot begin to model a human being and all of the multiple scales at the level that we would need to be truly predictive and to drive that kind of decision making. And when it comes to engineering systems, or when it comes to applications in climate modeling, again, it's exciting to think about what we could aspire to with digital twins, but we also have to recognize that we are very, very far from being able to simulate a complex system like a full aircraft, like a rocket engine, like pick your favorite system at the scale needed to truly represent the entire system and to drive predictions with the confidence we needed. So we call this out, that it's really important not to confuse the aspirational from the actual, because there are serious research questions that need to be addressed to move the frontiers forward so that we have some chance of digital twins having the impact and fulfilling the promise that they have. All right. Another key part that I think is very important, and I think this is particularly relevant to national security implications. But by the way, one of the themes you're going to hear through this talk is that I have come to really appreciate over the last few years how domains and applications that seem very distant from each other are actually have incredibly similar challenges. And this, by the way, came through the report process, but through many things. But this topic of verification, validation, uncertainty quantification, this was perhaps the topic that came up the most in every imaginable discussion that people would, it would be framed in different ways, but you can build me a digital twin, but how can I know I can trust it? This is a huge question, and this is a question where I think there are just fantastic research challenges and opportunities for the research community to really think about methods and algorithms that advance the state of the possible. So the definition here, verification, validation, uncertainty quantification, these are definitions that are fairly widely accepted and existing in the community. And of course, this is not a new topic. This is something that has been in large part led by the Department of Energy, a big focus of VBUQ for simulations and for model-based predictions. But now as we come back and we think about the digital twin setting, as I said before, it's more than just doing verification, validation, uncertainty quantification on a computational model. It's thinking about how VBUQ wrap around all of this, where now we have a virtual representation that's going to be changing. It's going to be dynamically updated. What does it mean to do verification and validation in that setting? We may have a human in the loop when we're asking the questions about the validation. Is the model good enough? It's not just about making predictions. It's about driving decision making. So all the questions we would ask about VBUQ of our models sort of get compounded and blown up as we put them in the digital twin setting. So this was actually the focus of one of the recommendations, was the second recommendation out of the study, which is it's not good enough to build the digital twins now and say that we'll worry about VBUQ later, that we have to get VBUQ baked in, really deeply embedded right from the beginning. And maybe said another way, I don't want to call it a mistake, but the way that we created simulation models, a lot of these models were created and then there became a realization, oh, geez, we need to really also understand how good these models are. And then there became a big effort of engaging with the statistics community and bringing in VBUQ formally. Let's not get it wrong with digital twins. Let's bake that in from the beginning, which means that we need new methods. We need new methods that think about the digital twin setting. A particular challenge is that AI and machine learning have to play a central role in digital twins if we think about all the needs here. But there are particular VBUQ challenges, particularly if you're going to have a model that has some kind of a stochastic element in it. And further, the challenges are that culturally, VBUQ is just not a big part of the machine learning community, right? It's okay to publish a paper where you get results that are a bit better than the other method, but whether you can validate or verify that for something like an aircraft or a medical decision where people's lives are at risk, just not really a part of the culture. So there are real challenges there that have to be taken on. And so we recommended that VVUQ be front and center. And I know there are statisticians here, Laura being one of them. A partnership between statistics, mathematics, computing, computer science, and the domain expertise is absolutely essential for making this so. Okay, the last sort of research need or gap that I want to highlight is tied to this finding in the report, which is that a digital twin should be fit for purpose. So what do we mean by that? One of the interesting things was from some communities, we heard a digital twin is only a digital twin if it's an absolutely exquisite replica of a system down to like the last detail. And then from other communities, we heard a digital twin is only a digital twin if it's a surrogate model that runs in real time on board a system, right? These two things are in complete opposition. So what we concluded was actually a digital twin, but could be either of those things or something in the middle. It should be fit for purpose. You have to think about fidelity for prediction and decision. How good is good enough? If you are a clinician and you have a cancer patient who is going to die and you need to make a decision about treatment, how good is good enough so that you make a better decision or that you have confidence in the decisions you're making? You need to think about available resources. How much time do you have to make a decision? If you are in some kind of a threat assessment and you have a digital twin of a complex system and you have hours to respond and your digital twin takes days to come back with the answer, it is not going to be useful. So available resources in terms of time to decision and computing resources, which may be on board or in situ on a system. And then acceptable costs. Was talking with the students yesterday, just like any technology that has to buy its way on board an aircraft, digital twin is just the same. If the costs to develop, deploy, and maintain a digital twin outweigh the benefits of having that digital twin, just doesn't make sense. So all of these things need to be considered, recognizing that different digital twin purposes are going to drive different fitness requirements. So where is the research in all of this? How do we tell whether a digital twin is fit for purpose? First of all, we're going to have to come back to verification, validation, uncertainty quantification. If we can't quantify uncertainties, we don't know how good something is. And then even if we can get a handle on the uncertainties, we need the methods that then go beyond that to help us drive decisions of, for example, how do I pick modeling fidelity? If I have an array of, you can think about the hierarchies in computational fluid dynamics, LES, RANS, even more simplified models. How do I pick modeling fidelity? How do I know how fine of a grid to run? And how do I do all this in an adaptive way so that as this digital twin is evolving, I could be going up and down my levels of fidelity or doing adaptive mesh refinement, sort of all the now nitty-gritty computational science and computational math technologies all have a really, really big role to play in making this idea of fit for purpose a reality. So I think this is another one where if you really sort of pick up and look under the hood, you see many, many statistical, mathematical, and computational challenges, all frontiers that have to be advanced to make digital twins fit for purpose and therefore useful. All right, before I leave the report, I had to pull, if you're reading the report and you get to page, 109, you will see CMDA got a call out. I may or may not have written this section. So there's a section in the report. It wasn't really part of our scope, but we had a little bit talking about education because all the magical research in the world is not going to do anything if you don't have the workforce and the students who are trained across the interfaces. Because I think everything I've said, I've already mentioned so many different possible majors. I am a huge fan of the CMDA program. I think it's a shining example of how you start to educate undergraduate students across the interfaces. The CMDA students are exactly the kinds of students that have little bits of all of these ingredients and could put them together that we need to advance digital twins. So CMDA there got a call out. All right, so now I'm going to switch from talking about sort of the high-level motivation and some of the Academy's things and tell you a little bit about some of the work going on in my group And so we're doing lots of things around digital twins. We have a big component of work that's around surrogate modeling and reduced order models because, of course, putting all this together, solving inverse problems, solving optimal control problems, all with uncertainty quantification embedded, maybe doing it in real time on board an aircraft. This is a tremendous computational challenge, and we are going to need reliable reduced order models and surrogate models and multi-fidelity formulations. So we have a lot of work in my group that goes on in that. I'm not going to talk about that today. I'm going to talk about the work where we've been trying to think about graphical formulations. And the reason I picked this one is because these are topics that are not terribly familiar, I don't think, to the computational science or computational math community. But of course, graph and graph-based models underpin so much of what is going on in the computer science world. And I think there's really an important set of connections that we need to make there. So so this is a snapshot of the cover of Michael Jordan's 1999 book on learning and graphical models. And I love this quote: "Graphical models, a marriage between probability theory and graph theory, provide a natural tool for dealing with two problems that occur throughout applied math and engineering: uncertainty and complexity. Fundamental to the idea of a graphical model is the notion of modularity. A complex system is built by combining simpler parts. Probability theory is the glue, ensuring that the system as a whole is consistent and providing ways to interface models with data." Michael Jordan could have been talking about digital twins, right? This is 1999. The term digital twin wasn't coined until 2010. But as I read this, I think about a digital twin, and I come back to this question: what makes a digital twin more than just simulation and modeling? It's that bidirectional interaction. It's that interface between models and data and decisions. And what's special about graphical models is that they emphasize relationships. The relationships, the edges in the graph, are just as important as the nodes in the graph. So this is, I think, a really sort of critical and powerful construct for sort of asking the question: how do we even begin to think mathematically about a digital twin? How do I write down and define the digital twin? And then, of course, you add to that all the advances in methodologies, in computational algorithms for graphs that could build on that. So the way we approach digital twins is we use a multi-layered graphical formulation. And coming back to Michael Jordan's quote, we're thinking about complexity and uncertainty quantification. So again, now I'm talking about my own viewpoint, my own research. I absolutely believe that UQ has to be baked into the digital twin from the beginning. It makes the problem much, 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 much harder. But standing up deterministic digital twins that just say, do this, with no context, with no quantification of uncertainty, just don't think it's the way to go. So embedding uncertainty quantification and managing complexity. If we're going to really get to digital twins of the kinds of problems we care about, it's going to be more than just a PDE written down with its initial conditions and boundary conditions. It's going to be more than just a nice, clean problem statement. It's going to be a representation of a system where there's all kinds of stuff there. Yes, a PDE that might be a mathematical model, but a whole lot of other bits and pieces. So we're trying to really tackle those formally with graphs. We think about a foundational level. There are a lot of challenges and needs, the kinds of knowledge, the kinds of data that you may need to embed, how interconnected the system might be, the fact that you need to think about this bidirectional flow between physical and virtual, to really think about how data provenance, knowledge integrity, these are all the things that, by the way, you don't think about when you solve nice, clean problems, but these are very, very real challenges for the real world. So here we use knowledge graphs as the foundational layer. And again, a knowledge graph is something that I had often heard about, really didn't know anything about. I don't think it's a tool that's often used in the computational science or applied math community. But really, what is a knowledge graph? It's a mathematical structure that lets us start to organize the information about the digital twin. So, here just as an example, if I were thinking about creating a digital twin of an unmanned aerial vehicle, I need to start first thinking about what are all the bits and pieces that I'm going to need to model. I'm going to need to model components, sensors, measurements, parameters of the physical system, parameters of my virtual representation of the system, quantities of interest, things I might want to predict, decisions, control actions, right? I'm going to have all these different elements. And I also need to think about how the different elements of the system are created. A sensor generates a measurement. A component might be instrumented with a sensor. So this is what a knowledge graph does, is it formalizes what you might otherwise write down as a problem statement in kind of a linear way. So this sort of defines an ontology with different entity types, those are the nodes, and different relationship types, those are the edges in the knowledge graph. Here's an example of that applied to an unmanned aerial vehicle. And one of the nice things about representing things as graphs is that then you can start to do automated analyses. So things like analyzing the graph to say, are there any illegal cycles? Have I set things up so that my vertical stabilizer contains a rudder, which contains a control system, which contains a tail, which contains a vertical stabilizer, right? So looking sort of automated ways for traversing the graph and looking for misspecifications. Okay, so we have the knowledge graph. And again, this is something we wouldn't normally do. And I should say the example here is for an unmanned aerial vehicle. But where we really started doing this is because we've been doing a lot of work, not a lot of work. We have one project with the Texas Higher Education Coordinating Board where we're trying to build a digital twin of educational system of actually student pathways for students who start off in community colleges and want to transfer into four-year institutions. So that's where we really started recognizing that we needed to have this knowledge graph layer. Where things start to get a little bit more comfortable for me is now when we come to the predictive layer. So this is a second layer in our digital twin. And in the predictive layer, this is where we really want to embed uncertainty. And when I say uncertainty, I mean uncertainty in everything. The uncertainty in the physical world, in the sensor measurements that you generate, but also the uncertainty in the digital world, because we know the models are imperfect and that there's all kinds of misrepresentations and uncertain parameters in the models. So model form there, the fact that we even know the models are in many cases wrong. And so in this predictive layer, we use probabilistic graphical models. So this is a graphical structure that represents not just the relationships between the different pieces of the system, but also encodes uncertainty. So in a probabilistic graphical model, in the graph, the nodes are random variables, and the edges, which represent the relationships between those two random variables, are conditional probabilities. So some of the early work, and this was Michael Kaptain's PhD thesis. Michael was my last PhD student at MIT. We really worked on how to architect and think about a digital twin as a probabilistic graphical model. And so I'll walk you through quickly, just sort of through this example. We identify physical states. What are the physical aspects of the system that you want to track? And in the probabilistic graphical model, we are representing those physical states. And here, this is discrete time. So at t equals 0, t equal 1, some current time, t equal 2. And the S's there are the random variables representing the physical state. So you could think about the structural health of my aircraft. And again, the edges are the conditional probabilities that in this case are representing the transition from state S0 at t equals 0 to state S1 at t equal 1. I'm going to also stand up and define the digital state. So this is now how I'm going to represent the physical state of my aircraft in my digital models. By the way, this will be, for us, we're model-centric. So we have the governing equations governing the structural dynamics of the aircraft wing. And so these digital states are going to be the parameters of those physics-based models. So the physics and the PDEs are still here. They're just kind of hidden in this graphical view. So we have here the digital state. We can now introduce the observations. So these might be the sensor data that we can collect from strain sensors on board the wing. And now as we start to build out the graph, what we are looking at here is the inverse problem of given observational data, O0, can I infer my representation, my digital state D0, that is a representation of my unobservable, or not, maybe not directly measurable, indirectly observable state S0, and also representing the transition there in time. So it could be a data assimilation problem. We can introduce the control actions. What are the decisions I can take? Can add those to the graph, those also in the physical world. We can think about quantities of interest. What are the things I might want to predict? And again, I want to emphasize the models are still here. Given the digital state D0, predict for me maybe maximum strain or maximum stress on the wing. So executing and computing this conditional probability means running a physics-based model. It's still here. And we can also introduce our objective functions, the notion of rewards. How do we measure decisions? How do we know whether they're good or bad? And we can also think about what happens as we start to predict out into the future. So now we have more elements of the graph, but now you notice that the control actions are in the digital space because these are things that we haven't actually yet done in the physical space. But again, we can build out the graph. And don't pay too much attention to why an arrow goes from one to another. You could imagine different topologies of this graph depending on how you wanted to represent it. But the idea is that we have now taken all the pieces of the way we represent the system, the governing equations, the data, the inverse problem, the decision problem, and we've represented it in the language of probabilistic graphical model with uncertainty embedded everywhere. So if you like to, I don't, but if you do, like to think about things this way, you could think that really what the digital twin is a giant joint probability distribution that encodes the relationships between digital states, quantities of interest, rewards, and future actions, all conditioned on past data and past actions. It's really what we're doing, is we're saying the digital twin is a giant joint probability distribution. And once we think of it in this way, we can now put our favorite methods on top of that to solve the inverse problem, to solve the control problem, to solve the data assimilation problem, all while incorporating uncertainty. Okay, so this slide says just the last sentence I said, putting everything on top. I won't go through this in detail, but as you start to think about the use cases, whether it's doing some kind of like a calibration to make the digital twin patient-specific or asset-specific, whether it's a forecasting problem for predictive maintenance, whether it's some kind of a decision or a trade-off, I like to think of this as like lighting up different parts of the graph or accessing different parts of this joint probability distribution. And what that means is that you're kind of pulling out different factorizations and different parts. And again, we're not yet dictating what kinds of methods. You could use your favorite optimal control method, which could be to solve some kind of optimization under uncertainty problem with your favorite risk measure, or you could decide to use reinforcement learning where you're formulating things as a dynamic programming problem over a finite horizon, and so on. Okay, so I mentioned here's a picture of Michael. This was work that Michael did in his thesis. We also have an unmanned aerial vehicle, physical vehicle that we designed and built together with Aurora Flight Sciences. And so Michael's thesis really sort of developed this probabilistic graphical model and built a structural digital twin of the UAV, kind of showed how one could go through all the calibration and then use the digital twin. Our target use case was to do dynamic mission replanning in response to structural health changes on board the vehicle. And so this was a situation where we needed the digital twin to be able to do dynamic updating and informing decisions in real time, which is where the reduced order modeling came in as a really rapid capability. Some of the work that we've got ongoing, and again, just to sort of emphasize, why take all this time to form the probabilistic graphical model, right? We could have just started building the structural digital twin of this UAV and we would have had it more quickly. But taking the time to sort of lay this foundation means that you now have a representation where you can do all kinds of other really, really neat stuff. And one of the pieces, and this is really ongoing work, is Well, it turns out there's a whole community of people that do formal verification, right? As a big thing, flight control systems on board an aircraft, formal verification, model checking. So it turns out that once you have formulated your digital twin as a probabilistic graphical model, one of my current PhD students has shown, and you'll see it on the next slide, that we can take that representation, get a finite state machine representation from, sort of extract it from the probabilistic graphical model, and then apply the model, the formal verification methods. And, again, we could ask the question, well, what's new here? People have been doing formal verification of systems for a long time. Well, digital twins bring new challenges. You start to think about, back to that diagram, we have the models, we have the dynamic updating, we have the decisions. So not only do we have to verify the pieces, we have to verify the digital twin as a whole. And we need to ask and answer really important questions such as synchronization. What happens if a sensor reading comes in, there's a lag, especially think about digital twin of a spacecraft. With your communication channel, you have an issue, you get sensor readings out of order, and you're doing your fancy Bayesian updating of the digital twin, and you don't realize the sensor readings are out of order. What's going to happen when the digital twin starts executing control? These are all the questions that formal verification looks at. There's also, I think, a really interesting potential connection between verification and security and privacy. So the questions you might ask about how does the digital twin act under these different circumstances of things that could go wrong? What if things go wrong because somebody has intercepted your data flow and is feeding your digital twin with some kind of compromised data? Or what if you want to ask questions about privacy? If I'm communicating different aspects of the digital twin and those bidirectional flows, and someone were to intercept it, what is it that they could reverse engineer about my system? These are all questions, by the way, that have very, very deep mathematical elements to them. So this is Luwen. Luwen's a current one of my PhD students. She's doing a PhD in computer science at UT Austin. As I mentioned, she has been taking the probabilistic graphical modeling foundation and then sort of putting a finite state machine formalization that sits on top of that. So that's the abstraction methodology, and then looking at some of these questions. We're also collaborating with Lab Varshney at Illinois, who is an expert in information theoretic approaches to, again, look at some of these questions about security and what that might mean. So I think this is a hugely important topic that is one example where there are communities who have long worked on these kinds of questions in different contexts. Thinking about what those questions look like in the digital twin setting, I think is very, very important. All right. In the last part of the talk, how are we doing on time? Yeah, it's good. I want to show you a couple examples, and along the way show you also some of the other sort of methodological pieces that come together. So we have right now a SURI. So this is a Space Force University Research Initiative project that we're involved in. I had always spent my career working on aircraft and aircraft engines, not really done too much in spacecraft, but it's been really great to collaborate with experts who in space systems, because again, as you think about the digital twin paradigm and what it could mean for being able to better manage assets in space, it's really, really exciting. So we have in particular been thinking about autonomous on-orbit operations. So these could be, for example, servicing missions where you might have some kind of asset up there that's broken down or uncooperative for some reason. And so you want to send in another spacecraft called here the Chaser. The first needs to rendezvous. Then when it rendezvous, there's going to be a capture phase where the two spacecraft actually need to come together. And then ultimately there might be some kind of on-orbit servicing or maybe a towing and a decommissioning of the target spacecraft. So this is a really, really challenging problem. It's an example where, we're sort of, these circles all look the same size, but you've got to look at a problem with very different scales, because when you're doing the rendezvous, there's no way that you can or want to model every spacecraft down to the finest level of detail, right? Because your models would just be so complicated and wouldn't run. So you kind of want to take the step back and look at these spacecraft and perhaps represent them as with relatively simple models in this phase. But as you start to get to this capture phase, this is a phase where just rigid body models are not good enough, because it turns out the moment that there's some contact, you get all the contact dynamics, very nonlinear interactions that come from the mechanics that need to be modeled if you're actually going to get the capture phase right. So I think this is a great example where, going back to something I said earlier, this ability to have the digital twin be fit for purpose, and recognizing that one digital twin is going to need to be able to model a system at different levels of fidelity and resolution. And somehow, as we're doing all of, again, this fancy Bayesian inversion and optimal control, we need to be able to zoom in and zoom out of the system so that we can get the appropriate level of fidelity and appropriate computational cost in this problem, all while doing quantified uncertainty. So this is a really interesting problem. Again, we can reach for the probabilistic graphical model, this formalism, where we think about physical states, observations, and controls, digital states, quantities of interest, and rewards. And they're different to the aircraft example, but you can go through this process of saying, what is it I want to be able to track? What are the decisions I need to make, and what can I measure? And how do I map all this into the graph that represents the relationship? So we've done that. And this is my student, Sebastian, who's a PhD student in the Odin Institute's Computational Science, Engineering, and Math PhD program, who is working on this. One of the key pieces of Sebastian's work is that we're really trying to think about this question of modularity. And again, we can remember Michael Jordan's quote about modularity, which is, yes, we could build a digital twin for the whole system, or maybe we could build a digital twin for the chaser spacecraft and another digital twin for the target spacecraft. But it turns out, if we really think about it, and we also really look at the way that spacecraft are designed, there's so much modularity and different pieces. So here are the different subsystems, if you like, of a spacecraft. How could we think about building digital twins at the subsystem level, and then having those subsystem level digital twins communicating so that we're getting a coherent, consistent representation of the entire spacecraft? So why would you want to do this? There's so many reasons. One is to manage computational costs. So you can start thinking about, what happens if something's going on in the propulsion system? Can I update the propulsion subsystem digital twin without touching the whole rest of the graph that's not affected, but then recognizing that this is coupled, and by the way, the graph is going to tell us how that coupling is induced. And so I'll need to understand what the impacts are going to be on the other subsystems and then how that propagates up. So turning what would be a monolithic digital twin that might be a computationally intractable task into something computationally tractable is one motivation. A second motivation really just ties to the culture, right? Different groups manage different parts of the system. They have different ways of thinking about their subsystem, different models. If we can reflect that modularity in the digital twin, then we sort of are fitting into the culture of the way that spacecraft are designed and even operate a little more. And again, there are so many mathematical challenges here of how you do it, how you deal with a coupled system. You break it apart, you make changes in one piece of the system, how do coupled sensitivities flow through? What does it mean for uncertainty quantification? How do you do a Bayesian inverse problem on one piece of the system and cascade its effects? So many mathematical and statistical and computational challenges and how you do this. But I think this notion of modularity is really important, again, if we're going to get digital twins of truly complex systems. I'm going to skip over this because I'm running a little late. So we have some initial work where we've just been looking at a pretty simple initial example where there's a failure in the propulsion system of the chaser aircraft as it's coming in. And the question is, how could you have health-aware control systems on board so that the digital twin could be responding to first of all, diagnosing a failure in the propulsion system, updating the effects on the kinematics, and then translating that into a health-aware control system. But let me, this is going to be the last part. I have maybe just 5 minutes to cover it. I also want to tell you a little bit about the work that we're doing in digital twins for cancer patients. And I have to ask, are there any medical doctors or biomedical engineers here? Oh gosh, that's such a relief. So this is great. I give the disclaimer, which is you are going to get an aerospace engineer's version of tumor dynamics. And I'm sure I will use some of the wrong words. But one of the reasons I like to highlight this one is, first of all, I think this work is a wonderful example of what happens when you have an interdisciplinary environment like you are building here at Virginia Tech. When you have aerospace engineers, mathematicians, and oncologists talking together at coffee hour, these are the kinds of, this is the kind of research innovation that can come out of it. That's one thing. And second, it turns out, as somebody who took, I think I did biology, had to do biology first year of high school, and then that was it. And it was not my favorite subject. It was probably right alongside English. I'm not sure I was supposed to say that while being videoed. And so when the oncology group approached me and said, you know, we're really interested in digital twins. We've been reading your paper about structural health monitoring of the unmanned aerial vehicle. We'd love to work with you. I was like, I think you've come to the wrong aerospace engineer. Turns out the analogies between cancer patients and aircraft, or, you know, just the analogies are so incredibly powerful and actually much more explicit and specific than you would recognize. And of course, it shouldn't be a surprise because mathematics is the universal language and mathematics binds all of these. So what is the specific example that we have been thinking about? And I should say now, out of all of us, actually have a couple projects going on. We have a really great collaboration with MD Anderson Cancer Center, which is part of the UT system. And I have one of my PhD students, one of my research scientists working actively on this project. But this is also a great story for digital twins. If we could think about high-grade gliomas, this is a brain cancer that's particularly aggressive. And what we're looking at here is the standard of care. So this is sort of the standard treatment. We're looking post-surgery. So after surgery has been done to cut out or remove as much of the tumor as possible, there's an image taken on day 0. This is right after surgery. Patient has a bit of time to recover. On day 20, there's another image taken, and then radiotherapy starts. And each one of these little purple bars here is 2 grays of radiotherapy given on Monday, Tuesday, Wednesday, Thursday, Friday, then no radiotherapy on Saturday, Sunday. Then you get 2 grays per day for the next week 2, week 3, week 4, week 5, week 6. So in total, this patient, the standard of care, patients get 60 grays of total radiotherapy delivered in this way. And then at some point in the future, day 152, there's a follow-up observation to kind of see what's happened. So it probably doesn't take too much knowledge in biology to imagine what a digital twin could do in this setting, where, again, image right after surgery, an image on day 20. First week of radiotherapy, 2 grays per day, Monday, Tuesday, Wednesday, Thursday, Friday. Then imagine we could take another image here, and we're going to need another image here because we want to calibrate, we want to build not just the patient-specific anatomy and the initial conditions of the tumor, but we also want to calibrate the patient's response, right? So we've been applying control here, and we want to take another image to see how effective that control has been. And so what we're doing here is building this patient-specific model where the material properties, and this is where the analogy starts to come in. Turns out the state-of-the-art of models of tumor growth are reaction diffusion equations. By the way, we do a lot of work with the Air Force and rocket engine reacting flow modeling, reaction diffusion equations. The reaction terms are different, but these PDEs. The big uncertainty comes from the initial conditions, the boundary conditions. The variability from patient to patient comes in the anatomy, the structure of the brain, because it's the tumor is reaction diffusion, but then there's also the elasticity model, the nonlinear elasticity model, because of the structural pressure from the brain. So the anatomy, I would call it geometry, initial conditions, boundary conditions, and then the material properties. I probably make some joke about white matter and gray matter, but material properties, I mean, they have different names, but they're akin to like our Young's modulus, our structural and material properties in the aircraft wing that need to be calibrated. So tremendous amount of uncertainty. Just like in the aircraft example, we can take measurements on the surface of the wing and we're trying to infer what's going on and the structural health on the inside. It's just the same here. MRIs, the images from the outside trying to infer what's going on in this very complex process. And so building the patient-specific digital twin and then having radiotherapy dosages that are tailored to the specific patient, but also being dynamically adapted depending on how things are going. So that's the vision. Again, this is the aspiration. We are very, very far, as a community, from being able to do that. So let me give you just, it's 11:28, a couple just quick snippets of what we're doing. So Anirban is my research scientist. So again, probabilistic graphical model, again, the states, the inputs, the observations, they're all different, but the mathematical foundation, I mean, just carries over beautifully. The bidirectional interaction of the digital twin, one thing that's really interesting to me is that there's a real OED problem, which is the question of how much value does an additional image bring? And if you were going to do an additional image, when is the best time to do it? Because if you wait longer, you will gain more information about the patient's response and material properties, but you will have less time to react and adapt the control plan. And if you do it sooner, you're not going to gain as much information, but you'll have longer to adapt. So there's a really great and interesting OED problem that my student Graham is looking at. So Graham has been building full 3D models of this brain setup. The imaging data, there are all kinds of imaging data that come in. You probably read in the newspaper that AI is revolutionizing imaging. Yes, AI algorithms can do a lot for imaging, but at the end of the day, the data are sparse, noisy, and incomplete, and there has to be a model sitting at the center of this. So there's that reaction diffusion model for the tumor. So just, again, just a lot of pieces that have to come together, but really drawing on everything I've talked about. So let me go over, there's a lot of details to get right about how you put all the different sources of images together, how you manage mesh generation, how you manage computational cost. Maybe I'll just show this one as the last one because it's got some eigenvalues in it, which eigenvalues are one of my favorite things. So Graham's been doing all of this at scale, running at TAC at our supercomputer center, building on some of the really great software that's out there for solvers. I think, Johan, you're here, you worked on PETSI, right? Did I see Johan somewhere? Yeah. So, again, and maybe just to come full circle back to the math, we're posing all of this in a Bayesian formulation. So we're solving a large-scale Bayesian inverse problem to invert for those unknown parameters. Those parameters are discretized on a full 3D grid, so we're talking about thousands or millions of parameters. So you've got to bring to bear all the state-of-the-art and scalable Bayesian methodologies, which means we use a Laplace approximation. It means that the Hessian, everything has to be instrumented with adjoints. It's really important to have adjoints if you're going to have scalability to high-dimensional parameter spaces. But the Hessian of the inverse problem plays a key role. And in particular, the spectrum of the Hessian, the eigenvalues play a key role. And in the particular setting and the way Graham's formulated it, what we're showing here is the eigenvalues of the Hessian, imaging fortnightly, imaging weekly, imaging daily. And so you can really start to quantify how much more information are you getting by adding in images. And what's more, you can look at the decay of the eigenvalues, but then you can also start to look at the eigenvectors. And again, as you would expect, the eigenvectors are going to tell you what are the directions and parameter space, what are the fields that are being informed by the data. And as you image more frequently and you're changing the eigenvalues and the eigenvectors, you're getting insight. And as you would expect, right, you're getting insight into different modes and different configurations. You can now then get back with the oncologist and start to look at these modes and say, what's really going on here about the tumor dynamics. So there really is this beautiful back and forth, I think, between the math and in this case, the domain science. All right, with that, I had a couple of slides of conclusion, but I'm going to finish just on the last slide here, which is, again, there's a lot, and I know I threw a whole lot of pieces at you, but that's the wonderful thing about digital twins, is actually, in many ways, I feel like they're like the integration of my career. It's, I think, amazing what we can start to do today and we're already starting to see some digital twins having impact in some applications. But the best news of all is there's so many opportunities because there are so many challenges. And I have just, some of the things that I think about that as being on the critical path for digital twins. So some of my favorite topics like reduced order modeling, surrogate modeling, large-scale inverse problems, and uncertainty quantification. But also other things like human-computer interaction, visualization. These are areas that have traditionally not been well integrated with applied math and engineering. If we really want digital twins to have impact in the clinic, in the engineering world, we're going to have to start integrating these. So it really is a scientific grand challenge, and I think it's pretty exciting. So with that, I'm sorry, Justin, for running a little long, but let me stop, and I'll be happy to take some questions.